Going to live. Okay. Hello, everyone. That's me without a head. Hang on. So, we're off to the races again tonight. We have new gloves that go down our wrists. We had, for a while, another kind of a cover. And then I discovered that you can't run an iPhone without a fingerprint. So I am now exposed to the UVC light in a very small portion. So ET phone home. This is how we're going to do it. This is getting more and more like sci-fi and less like science training. But hey, that's how it goes. Tonight we're going to have David demonstrate his prowess around laboratory equipment. So we're going to go through a bunch of that. And for some of you, it'll be a first time around chance to actually put names to all that neat gobbledygook that you've been seeing back in the labs. So with no further ado, I'm going to invite David to come on up here and begin to present. He's plugging his air hose in right now.
It's a little bit high up even for me. Okay, so we're going to cover the different laboratory equipment that we use, and I wanted to start with a refresher. Some things that we already covered last time. Can somebody tell me what this is?
Micropipetter?
Correct. Exactly right. That is a micropipetter. We have 3 different sizes, and I fixed them so that the color of the cap tells you the size, but you can also read it on the side. And of course, these micropipetters you have to use with the pipette tips that are designed for them. If you have the larger ones, it's this type of pipette tip. And recall that when you're first getting your liquid, you push down to 1 stop and let up. Keep it in the liquid for a second after you let up so that you don't draw in an air bubble. And then to dispense it, push down to 1 stop and then down to the 2nd stop. Okay? Anyone remember what this is for?
That used to eject the tip.
The little button out to the side.
It used to eject the tip.
Yeah, that came as a whisper to me, but yes, it's to eject the tip so that you don't have to use your hands.
Could I have Vasu? Could you give me a count to 3 on the home side?
1, 2, 3.
Okay. Yeah, Rishi, you're a little soft tonight.
Okay, now a harder question. Anyone remember what this is called? Has gradations up to 10 mils in this one. It's not a micropipetter.
It's the glass pipette.
Sometimes they're glasses when it happens to be plastic, and it is a pipette. Now the name for it, like I said, this is a harder one. It's a serological pipette, but that's not really important in my mind. To use the serological pipettes, we use pipette fillers, and we have 3 different sizes for different sizes pipettes. They have the knurled knob we call for pulling up the liquid or pushing it down to dispense the liquid. And this one has this trigger on the side. Anybody remember what that is or what it's for? Gee, you guys need to go back and review those previous lectures. Okay, if you push this, it dispenses all the liquid. Okay. Next is my favorite. There's another hard one. Anyone remember what that's called? It's named for the person that I think is the greatest scientist who ever lived. And remember, I'm a biologist.
Pasteur pipette.
That's correct. That is a Pasteur pipette. Okay? And Pasteur is my hero, so that's my favorite. This one, you have a detachable rubber bulb, allows you to pull liquid in and dispense liquid to transfer it from one place to another. And the fun thing with these is they're made out of glass, which means they're fragile, they break easily. But you get 2 of these over a burner, and you can melt the glass and start making little sculptures. Just be very careful. Glass stays hot for a long time, so you want to make sure you don't touch it. This one. Nope. Not that one. Where, oh where did it go? There was one more kind of pipette we talked about, and apparently it didn't make it out here to my table. But it's like the Pasteur pipette. It's plastic. It has a built-in bulb, so you don't have to add one to it. And it's called a transfer pipette. And sometimes you'll hear somebody say a barrel pipette. But usually when they talk about barrel pipettes, they're talking about really small ones, very short, very thin. Okay, to a different topic. This is called a ring stand. Why would it be called a ring stand? Because it's a stand and you can put a ring on it. So this is a ring to put on the ring stand. And here we have a clamp holder. Now that's a newer name they've used, and I don't like it because we used to call it a test tube clamp, which makes it very simple. And you have a screw here you can turn, and it'll close in and hold a test tube for you. Both of these are really great when you're heating something. Makes it easier for you to do that. And anyone know what that's called? Several of you have had chemistry, so you really should know these.
Can we zoom into it?
What's this part made out of?
Like wire mesh rack or
That's
something
correct.
like
This is wire, and this part they refer to as gauze. So this is wire gauze. Used to be asbestos, but we got rid of those because asbestos can cause a lot of harm. And this can set on the support ring, so when you're trying to heat up a beaker, you don't put it on the support ring because it's going to fall. Instead, you put it above the wire gauze, and that'll hold it in place. And you can go to fairly high temperatures. You don't have to worry about burning these. Anyone know what this is called? You have these in high school chemistry labs.
A Bunsen burner?
Almost. That's very close. Because this is a Tyrrell burner. And yet, your teachers probably called them Bunsen burners. The only difference is that with this one, you can change the flow of the gas. With a Bunsen burner, you had to turn the handle at the source of the gas coming out. This one, you can adjust it right here, much better. And then you have, both on the Tyrrell and the Bunsen burner, you have this little portion that you can turn and change the amount of air coming in. And when you're using a burner, you want to adjust the air properly. Well, the amount of gas you adjust to get a flame that's about 3-4 inches high. You adjust the air so that the flame is mostly blue. The bluer the better. Get rid of the yellow. Yellow indicates incomplete burning. Now when you have a flame, there will be 2 cones. And the tip of the inner cone is the absolute hottest part of that flame. That's where you'll want to have most things come to that point. The tip of the inner cone. Of course, at school you have a gas supply. We have propane gas here instead in bottles. Beakers. Most commonly used to hold liquids to work with them. Beakers need to either say Pyrex or Climax on them. That indicates that they are a stronger glass that's not going to break when it's heated. And I once made the mistake of not using a Pyrex glass test tube. Instead, I had a flint test tube, and in the middle of it, heating up as a demonstration for the students, it broke and dropped burning stuff onto the table, which was kind of embarrassing since the principal was there evaluating me at the time. But beakers come in a wide variety of sizes. I've worked with ones that are just teeny tiny 5 milliliter. I've worked with ones that are 10 liter beakers. So a wide variety of sizes available. Now, on the side of this beaker, there are gradations that tells you how much is there. Those are extremely unreliable. Never use those when you're trying to measure a certain amount of liquid. What do you use to measure a certain amount of liquid?
You'd use a pipette.
If it were a small amount, yes, you can use a pipette. Up to 10, 25 milliliters, I would say. I've never seen a pipette that went above 25. But what if you wanted 100 milliliters? How would you make? You don't want to use
Can you use a graduated cylinder?
Excellent. These are graduated cylinders. They finished high school. They graduated. This one, 50 milliliters. This one, 100 milliliters. And this one has this plastic ring around it. I like this one better because if this one falls over, good chance it's going to break. And in your high school classroom, this is probably the most expensive piece of glassware because they're calibrated. If this one with the plastic falls over, it tends to hit the plastic, works as a shock absorber, and it doesn't break. But when you're trying to measure a volume, you never go by what's in the flask or the beaker. Use a graduated cylinder if you want to have any accuracy at all. This is called a volumetric flask. On the side of it, it has a volume label. This one says 100 milliliters. That means, and there's a etched ring around it right here. So if you fill this up to where the bottom of the meniscus, which is what you always read with liquid, except for what liquid?
Mercury?
Yeah, mercury. That's the one you have to read the top of the meniscus because it bubbles that way instead of that way. And when you fill this right to that line, you have exactly 100 milliliters there. So if you're making up a solution, a lot of the times it'll say, add so many grams of this crystal, and then QS to 100. QS means to fill it up the rest of the way from Latin. And you use the volumetric is the easiest way to do that. Get exactly 100. This comes with a stopper with ground glass. You see very little ground glass anymore because they tend to stick, and it can get to where you're not going to get it out without breaking. So we don't use that much anymore. But a lot of times you make up a solution and you keep it in this for a long period of time because you keep using that very accurately made solution. This is a round bottom flask. It's not quite perfectly round, a little bit flat, so it will sit up. But a completely round bottom one is round all the way. And these are used for heating up liquids evenly because there's a thing called a mantle. We don't have one, but it's kind of shaped like the palm of your hand. And so it's electrical. You plug it in and it starts heating up. And then you can put the flask in there and it's going to heat it evenly around the edges, the surfaces. And if you do that a lot, chemists get to know where all they've got to do is touch the flask and they can tell what temperature it is pretty closely, 50, 60 degrees. It's convenient when a waitress brings you a plate and says, don't touch that, it's hot. I have to touch it. And then I'll tell her how hot it is. Although one time she said it was hot, I grabbed it in the air and I immediately dropped it because it was way hotter than what I could hold. And I'm pretty tolerant to higher temperatures. We have one more flask. There he is. You know what this kind is called?
Erlenmeyer flask?
Excellent. Yes, that's right. An Erlenmeyer flask. Again, the gradations are not accurate. They give you an approximate volume. But Erlenmeyers are commonly used. One of the reasons is if you're mixing a solution, you can swirl it in this and it tends to not come out over the top. If you're using an open beaker, much easier for the liquid to come out. Also used a lot in titrations where you're trying to determine how much acid or base a solution has and you're adding stuff drop-wise and you can keep mixing it as you're doing so. This device is a hot plate magnetic stirrer. And very, very convenient because you can use it to heat up a solution and you can use it to stir the solution. So we have these things called stir bars, sometimes called a magnetic stir bar. And we put this into a beaker and turn this on. I don't know how well you can see that, but the stir bar is turning. And so if you have something that you need to mix and it's going to take overnight, it's not very pleasant to have to stand there and keep stirring it. But the stir bar creates a vortex in the middle, makes things mix very quickly. And it'll keep stirring it as long as you want it to, unless your liquid gets real thick. And then the stir bar stops. Now you've heated something up on here and you need to move it. What are you going to use to move it? It's hot. And so we have these. They're called crucible tongs. Tongs designed to hold crucible. It's a crucible. Crucibles are usually made of porcelain. You have a small bowl and a top that fits loosely on it. And you put something in here that you want to get really, really hot. Put it over a flame, and after a while, the crucible will actually turn red, bright red, cherry red. And it's really, really hot. So to move it, you don't pick it up with your fingers. You use this. Now, some people will lift it like that. I find that occasionally they end up dropping them, so I prefer to use the very ends. Pick them up like that. However, these are very, very fragile, so you want to be careful that you don't break these. They're very easy to do. Oh, and crucible tongs can also be used to pick up an Erlenmeyer flask or other things. In our labs, I give the students a piece of magnesium strip, and they hold it in there and put it over the flame, catch the magnesium on fire. Another item that's porcelain is called an evaporating dish. It's used to evaporate substances to make them go away. So for example, I would have my students make a mixture of sand or dirt and water. And then they had to filter it. Well, how do you filter it? You use a funnel and filter paper. And there's lots of different sizes of funnel, different materials they're made of. We've got metal and glass. With filter paper, we fold it in half, crease it, fold it in half again, crease it, then open it up so that there's 3 sides on one side and 1 side on the other. And then it fits in there. And you can put this in your Erlenmeyer or something else. Pour sand and water mixture in there. The water will go through the filter paper and the sand won't. And you can get different grades of filter paper that will let through some substances and not others. And I also had the students use salt. So they had salt and water and sand. So what stays in the filter paper then?
Somebody be daring.
You've never done that experiment? Wow, you're so deprived. Sand's going to stay behind. Salt water is going to go through. The salt dissolved in the water. You can't filter it out. It's a solution. Solutions cannot be filtered. So how do you remove the water and the salt? Separate them.
Distillation?
Say again?
Distillation?
Oh, you could, absolutely. But it can be done even more simply than that by just taking an evaporating dish, put the salt water in it, and put it over heat. As it heats up, the water is going to come off, and the salt is going to stay behind. Now, if you use distillation, you can recover the water also. You're right. Perfect answer. Test tubes. There's a wide variety of test tubes, all kinds. As I said before, I prefer not even to own any Flint test tubes. I want Kymax or Pyrex so that they don't have any problem with the amount of heat we use. And you can get plastic ones. Of course, these cannot be heated at all.
They now have borosilicate.
Pardon?
They now have borosilicate.
Yes. Actually, I think that's what the Pyrex and the Kymax are. I know they have boron in them. Yeah, must be boron silicate. Okay, so I'm going to some water in there. And so plastic test tubes, of course, you cannot heat. Oh, let's use a different color. Let's be brave. Oh, that went a lot faster than I was hoping. Because I was going to show you that if you use what's called a vortex mixer, that makes it mix really fast and really well, and it becomes homogeneous. And it's turned on, all you do is push on it, and it gets going. And it's mixing that liquid up really, really well. For test tubes, we have different kinds of racks to hold them. Some racks hold them at an angle. We also have micro test tubes and micro test tube racks. This leads me to this device, which is a micro centrifuge. A centrifuge spins rapidly. And there are different kinds of centrifuges. This one's real small, micro. So why do you want to spin samples rapidly?
David,
Because-
could you move some of the things that are between it and the camera so that the
Certainly
people at
try.
home can see it? It's just the graduated cylinder. Yeah, those are the ones.
That work?
Yeah, perfect.
Okay. So very small tubes spin very fast. Well, when you spin things fast, they tend to separate. Now, are the denser objects going to go to the bottom of the tube or the top? By the way, the tubes are at an angle as they spin. They're like this. So where are the denser things going? Right, to the bottom. Exactly. And that's to do with gravity. One of the problems that I have in research is you'll read some paper and they'll say, oh, we centrifuged it at 6,500 RPM. Well, that's nice, but how much force was that? Unless you know the distance, 6,500 RPM doesn't mean anything. And a lot of times you end up just playing around with things, trying to find what works best. At one point, I was getting 4 liters of cow blood in a day, go down to the stockyards and get that, bring it back to the lab, put it in these big bottles into a huge centrifuge, spin it down, and you get 3 layers with blood. The top layer is going to be plasma, or serum, depending on whether you've got anticoagulants in there. The bottom layer is going to be very red. What would that be? What's red in blood?
Hemoglobin?
Yes, but actually we could just say red blood cells. And it's the hemoglobin in the red blood cells that makes them red. That's right. If you get blood cells, get your blood from a vein, what color will the blood be? Never had blood drawn, huh? You guys are young. I've had lots. I actually had a science teacher who had a master's degree in biology come and ask me if the blood in the vein is blue. It is in drawings because they draw it that way. In real life, it is dark red. And in arteries, which have fresher blood, it's bright red. Okay, so it's because in the hemoglobin molecule, the center of it, there's an iron atom. And if iron if that hemoglobin comes in contact with oxygen, it goes to the iron, and actually, for a moment, you get like iron oxide, rust, and it becomes very red, bright red. But the blood is always red. Okay. Spatula. There are many types of spatulas. This one is actually called a scupula, and it actually comes, the handle comes off. You can just use that part. And this one is called a micro spatula, so you use it when you're trying to get very small amounts. And these are just used in order to get crystals, powder, whatever, solids out of a container. And you don't actually measure with these. This is called a watch glass. And I would bet most of you have never seen a watch that has a bezel glass on it like this. But watches used to have this, and it was much smaller. But we use this in science. You can't heat these. These are not heat tolerant at all. But you can put something on there to see it more clearly, inspect it, and you can use it to let stuff evaporate slowly. You just cannot heat it. Who can tell me what these are? Okay.
Tweezers.
Things up with them. Excellent, but wrong. In real life, yes, everybody calls them tweezers. In the lab, we call them forceps. In surgery, the surgeon calls them pickups. But forceps is the proper name for them, and they come in a variety of sizes, a variety of styles. Some of them have special teeth for grabbing certain things. This is a mortar and pestle. It's used to grind up crystals, to make them into powders, and to make noises that really irritate some people. They're a little bit tougher than, say, the evaporating dish, but they can break. And I've had students prove that. Hard to remember which is which, mortar and pestle. The way I remember, I could take this and shoot somebody, bang, bang. So it's like a pistol, or a pestle. And this is a mortar, and if you ever watch somebody graduate, they wear a mortar board on top of their head. So this could be a mortar on your head, mortar and pestle. Now, if you're going to be heating things up, good idea, have a thermometer. You'll notice this one is red. That means that it has alcohol in it. If it were silver, it would have mercury. And it's hard to find those anymore, even in hospitals now, because people are concerned about mercury poisoning. Mercury is more accurate than alcohol in the thermometer. But these are fairly accurate. And you can also use it for measuring cold. I've done work with liquid nitrogen, dry ice, acetone, where we were cooling things down. And we use these to check the temperature, although with liquid nitrogen, it'll go, all the alcohol will be down here in the bottom, nothing up there. Oh, besides the stir bar, you also have stirring rods. They are simply a piece of glass, and that can be used to stir with. It's also useful for pouring. If you're pouring from one container to another, and you don't have a funnel, you can put the stir bar on the lip, and then when you go to pour, okay, just take my report. You go to pour, the liquid tends to follow the stir bar. These are tiny little glass beads. And we used to call them boiling stones. Now call them boiling beads. We used to use stones. But the idea is if you have something in a, say in an Erlenmeyer, and it starts to boil, it could very easily pop the liquid right out. So you have these in there, and they bounce around and absorb some of that energy so that you don't get a sudden rise in the liquid. This stuff, oh, my piece fell off. This is called parafilm, one of my favorite substances in the lab. It's a petroleum product, and you can stretch it. And then you can put it on something like, say, a beaker, to seal it so that nothing gets in and nothing comes out. That's parafilm. This is the rubber stopper. Many people will call it a cork, but we don't use cork anymore because cork doesn't seal as well. Rubber stopper seals very well. And you have to get one that matches the size of the opening. So this one would require a pretty big Erlenmeyer flask for it to work on it. And rubber stoppers all have numbers, and the numbers tell you how big it is. And we have a box of them with a variety of sizes in there. Some of the rubber stoppers have a hole in them, some have 2 holes in them. The main reason for the holes is you could take a glass tube and put it through the hole, and then whatever, say you were boiling something, as the gas came out, it would go through that glass tube and say into a collection vial of some sort. The problem is getting the glass rod into the hole. And I never, ever let my students do that, because it takes a bit of technique. You put a little bit of oil on the glass tube and turn and twist as you're pushing it in very slowly. Students have been known to push the glass rod right through their hand. And you really don't want that to happen. Here is a balance. Now, a lot of balances, especially in high school, have a pan, 2 pans on them, or 1 pan, and you move weights back and forth. And I fought for years to get schools to get rid of those. Go with electronic balances. They're so much easier to operate. A lot of labs that we would do, using what are called triple beam balances, would make the students spend the whole lab trying to weigh stuff out. It's so much easier with an electronic balance like this one. When you use the balance, you have to turn it on and don't touch anything until it stabilizes. And after a bit, it'll read 0. Now, this balance comes with a weight that's an exact amount, so you can put it on there and make sure that the balance is correct, the weight it's giving you. You also have on the back of it a level bubble. So you can make sure the balance is level. That's very important. Then when you're ready, you put an object on it. If it's liquid, you never put that on the balance. If it's crystals or powder, you never put that directly on the balance. So you put something there. Now, maybe it would be a beaker. And then you push the button that says tare, T-A-R-E, or 0. And it automatically subtracts the weight of what you put on there. Then you can put your liquid or powder or crystals inside that beaker. Now, when you're weighing small amounts, we have here weighing paper. It's what's called glassine paper, so stuff doesn't stick to it very well. And you use that for really small amounts. For larger amounts, we have plastic weigh boats, weighing paper and weigh boats. And if you have a large amount of stuff you need to weigh out, we have larger weigh boats. The one thing you do not want to do is put an organic solvent in a weigh boat. Anyone have any idea why? Okay, well, this is a plastic. Organic solvents dissolve plastic. I found out the hard way. I was working in an industrial lab and was told to weigh out some hexane, and I poured it in, and it just went everywhere. As it touched the plastic was gone. Okay, last time we talked about this. Anyone remember what that's called? Complicated name. 8 by 12. What would that mean? What would that equal? How many wells?
96.
96, good. 96 wells. This is called a 96 well micro titration plate. And you'll recall we put in different colored indicators with different pH buffered solutions, and they turn different colors. That's what a titration is, getting a change in color. I don't want to do that. Let's get just bought several boxes of Chem wipes. These are nice in the lab because they're small, good for cleaning up a liquid, and especially for cleaning off a cuvette, because they're not going to leave anything behind on the cuvette. Now, this is a cuvette, very, very tiny, and it's used in a spectrophotometer, which means that this one is actually a micro cuvette, and it has an area where light's going to pass through. You have to make sure you set it correctly in the spectrophotometer so that the light can pass through that area. If it tries to come through the side, it's going through a lot more plastic. Now, because we had problems with our spectrophotometer, we have purchased a new cuvette. That one was a disposable cuvette. Many people use it once and throw it away. This is not. This is very expensive, so you use it over and over. It has black sidewalls to help you not have reflection of light when you're doing it. So we're going to find out whether or not this one works better. It also is a micro cuvette. It's made for working with very small volumes. You don't have to have very much of your substance. Bacteriology. This is a Petri dish. And yes, I've heard some people from England say Petri dish, but it's a Petri dish. And usually you would put some growth medium in here. You would plate some organisms on it to grow, bacteria or yeast, and keep it sterile. Very important. Sterilize it before you put the stuff on it. And then you can check the growth afterwards, see what happens. There are all kinds of tests that you can run, and we'll be doing some of those later on. To put the organisms on the Petri dish, you have these funny things. Now this one's plastic, which means you can't heat it to sterilize it. It'll melt. This one is metal. The wire here that ends in a loop is nichrome wire. It's the same wire that's in your toaster at home. So this can be heated up very well. You put that in a flame, you get it to where it's red hot. That means there's nothing living left on there. And then you can let it cool, get some bacteria on it, plate it onto your Petri dish, or put it into a culture tube. Oh, the plastic one, you have to use alcohol and then let it dry to sterilize it. Or you buy ones that are already sterile, packaged that way. This is a microscope slide. Usually you need to clean it before you use it. And then in this box are tiny little cover slips. Microscope slides, a little bit fragile. Cover slips, very fragile. Now some are plastic, which makes it less fragile, but not as good optically, so you don't get to see as much detail. Glass ones are better for that. And the reason you have the cover slip, you have your slide, your specimen on the slide, the cover slip on top so that nothing will touch the specimen. Sometimes we want to look at things with a UV light. I haven't used this one, so I'm not even sure how you open it. Probably not that one. Now, these lights are UVC, higher energy, shorter wavelength, great for killing especially the viruses we're concerned about right now. This comes with special yellow goggles so that your eyes don't get hurt. This is working off of UVB, and it is quite strong in a small area. And sometimes you want to be able to see what happens with organisms when they're under UV light, especially if you're doing some of the genetics work today. The organisms, you can tell whether or not your experiment worked by whether or not they change color under UV light. Okay, that's it for all this equipment. I think I've covered every single one of them. And now we need the PowerPoint. Some of the equipment is a bit heavier than what I want to have to carry to bring in here for you. So I took some pictures of them with help. Most important tool in the lab.
Okay, you need to turn it on. Sighted the...
Oh. There we go. Is your brain. You need to be able to make intelligent decisions. You need to be able to keep safety in your mind at all times. But the most important tool in there is one that you bring with you, your brain. Anyone know what that is?
So it's scanning electron microscope.
Excellent. An SEM, scanning electron microscope. I have never, ever seen a high school lab that have one of those. Not a whole lot of colleges do. And yet we have one here. thanks to Carl and Adam. And they know how to use it. We need to learn. And I still believe it's black magic. And we have a reactor, a thermonuclear fusion reactor that our students built and our students run and our students use to do original research. That's so unique. We're the only one in the world. According to an article that was written in Spain about us, they said nobody else has this. And as fusion reactors go, ours is doing a lot better than most of them. What's that?
A fume hood?
No! No, please, no. We think of it as a fume hood because that's what you got at school. But fume hoods are there for one reason only. Any experiment done in them that produces a harmful gas, the gas goes outside so it can kill the people out there and not harm you in the lab. But that's not the purpose of this. This is a biosafety cabinet. There is a wall of air that comes down right there,
Okay.
going down.
Back up and try again.
Oh, really? All right. So from here down to there, it's a wall of air. And that air has gone through a HEPA or HEPA filter that gets rid of very, very small things. So the inside of that, as long as we keep it clean, we wipe it down with alcohol, it's sterile. So we can work with organisms in there and they won't get contaminated. And hopefully neither will we, because the organisms are inside a biosafety cabinet with an airflow that's keeping anything from coming out towards you. Which is why there should never be anything on that grill that would impede that flow of air. Now, the first time I worked with one of those, about 30 years ago, and my boss was old school, and he had me using a flame inside the biosafety cabinet, and everything I did got badly contaminated, really badly. And I was doing some important work. We were getting specimens from surgery, and they were all getting contaminated with fungi. And I was reading the instructions on the cabinet, and it said in there, do not use a flame. It messes up the airflow. And my boss said, that can't be. And I said, well, let me try it. So I stopped using the flame to sterilize in the cabinet. No more contamination. It made the difference. Microscopes. We have a few. Our big one that has the huge stand there and the screen up there, because it goes over through the picture goes through the computer and then gets put up on the screen. So we can magnify things pretty large. The microscope itself doesn't magnify very big. It's not intended to see really tiny things. But with the computer added to it, we can see protist quite well. Not so good for bacteria. And that's our new spectrophotometer. And we're still trying to figure out why it's not quite working right yet. But it's going to. It's a very expensive piece of equipment that I'm really happy we have. And you can use that to measure the quantities of very small things in solution. And it can be bacteria, chemicals, protists, anything like that, algae. That is an ultrasonic cleaner, also known as a sonicator. And you put wire inside of it, put your stuff in there, and it sends in sound waves and breaks stuff up. Used for cleaning jewelry and such, but we've used it for other things. Used it to break up our boron nitride nanotubes, which come looking like pieces of cotton. And after several hours of sonicating, they end up breaking up into solution. Well, not solution, but a mixture. And that's our oven, except that we do just low temperature, so it's actually an incubator. And we keep it set at 39 degrees, which is the best temperature for incubating most bacteria and protists. Not all, but most. And it's guarded. Anybody know who those guys are? Oh, we need to bring back the Muppets. Actually, I think they started making new Muppet shows. But that was over there. I can't. Yeah, that one is Beaker. And that is Dr. Bunsen Honeydew. That's our chemical cabinet, where we keep a lot of chemicals. And they're laid out in a particular way inside there. And that's for safety concerns. And we're going to talk about that later on more. Another microscope, we have 3 of these that will magnify to very high power. We use an oil lens on it, objective, and you can go over 1,000x and see bacteria quite well. And that's another one of these things. It's a centrifuge, except that one's a big centrifuge. It holds test tubes, and it's not that big around. Like I said, I've worked with ones that held big bottles, stand on the floor. But this works well for the things that we've been doing. And any chemist will tell you the most important tool in a chemistry lab is the periodic table. And we have a bunch of them. And we also have a bunch of ones that you can have if you want, because I acquired them. Unfortunately, I acquired them before we got these new elements down, the ones in the light gray. We had the elements, we didn't have names for them. And recently they've been named, and so I'm trying to get new periodic tables. And we get them from recruiters, Marines and Air Force and Navy. All the recruiters, well, I avoid the Air Force. Even though I was in the Air Force, they give the worst periodic tables. It's basically advertising just for the Air Force and nothing else. Anyway, periodic table, extremely important. You'll see it in any lab you go into. They're going to have a periodic table. It's important. Even though your brain is more important.
I go.